So in this video, I'll be going over the structure of an epsilon delta proof in the format of the limit as x approaches a real number does not exist. Okay, so I'll be using this one as an example. So first thing we have to note here is that this does not exist, right? So first, what does it mean when a limit exists? So let's say we want to say that the limit as x approaches a of f at x exists, right? How do we say this? Well, this just means that there is one convergent point in which, as x gets infinitely closer to a, the function converges at that point. But this point has to be a real number, right? Infinity does not exist. Negative infinity doesn't exist. So this is the same as saying there exists an L in the reals, right? We know that infinity is not in the reals because infinity isn't even a number, right? So there exists an L in the reals such that, the limit as x approaches a of f at x is equal to L. And of course, we can write this in epsilon delta form, like so. For every epsilon greater than 0, there exists a delta greater than 0. And then blah, 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 right? So now we want to say it doesn't exist. This is just saying the complete negation of the epsilon delta proof. So first, let's write this in exists form. So if it were to exist, we would say there exists L in the reals such that for every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than x, or in this case, absolute value of x less than delta implies that x over the absolute value of x minus L is less than epsilon, right? Okay, so the negation of this would be our want to show, and let's just negate it. So you should be familiar with how to negate statements like this. So if there's exists an L, we have to say that for every L, the rest is false. So we have to say, there exists an epsilon greater than 0 such that for every delta greater than 0, there exists an x in the reals, right? Because there's a hidden quantifier here that we also have to negate, such that, and we want this statement. So if we want to disprove a conditional, we want to say that, okay, there's a case where this is true, but this is not true. And that automatically disproves the conditional. So such that 0 is less than the absolute value of x, which is less than delta, and x over the absolute value of x minus L is greater or equal to epsilon. Right. This is our want to show. It's a very nasty want to show. And I would say this is probably one of the hardest epsilon delta proofs that you will probably encounter in Unit 2. But that's okay. We can take this one step at a time. First, we have to define L. Let L be a real number. And keep in mind that we have to prove this statement for every L in the reals. So we have to show that this is an arbitrary number. Okay, now we have to take an epsilon, right? This seems kind of weird. We're taking epsilon this time. This is why it's kind of confusing, because now we have to let delta be greater than 0. Like, it seems backwards, right? Because it kind of is backwards. And then we need to take an x as something, and and then we have to prove that 0 is less than x, the absolute value of x, less than delta, and we have to prove that x over the absolute value of x minus L is greater or equal to epsilon. This is the structure of our proof, and let's just take this very, very slow. And this proof might take a while to understand because it's not very intuitive until you really understand it. First, let's just draw this function. Before we do anything, let's just draw the damn function. When x is positive, right, we agree that it's just 1 over 1, right? Because when the absolute value of x is positive, it's just x. So we just have x. So we know that this is equal to 1. So we know that, okay, let's say this is 1, and let's say this is negative 1. We know that when x is positive, the function just goes like this, right? Obviously, at 0, it becomes 0 over 0, undefined, right? Same thing down here. And when x is negative, right, we have a negative x over the absolute value of negative x, which is just x. So this becomes negative 1, right? So then we have the function like this. And we can see that obviously the limit doesn't exist as it approaches 0. But why? So we're going to dive back into the logic of epsilon delta proofs, of explaining why we can disprove or prove our want to show. Okay, so we know we have a delta, right? And we know delta has to be greater than 0. And keep in mind that delta is just, in this case, we can just imagine delta as a distance from 0, right? And since delta is non-negative, since delta has to be positive, that means we can have either 1 as our value of x, of our function, x over absolute value of x, or we can have negative 1. Because even as you infinitely approach 0, you can still choose either the positive side or the negative side, right? Because this is also the absolute value of x. Keep in mind that. This is a very key point. Try to convince yourself that this is true. Since our delta must be greater than 0, that means if our x is in between those two, right? That means we can have an x. There exists an x. We can find an x where the function is 1 or it's negative 1. Would you agree that this is the same as saying x over the absolute value of x is not in the interval between L minus epsilon and L plus epsilon, right? This should make sense because we're saying that the function just has to exist anywhere other than this middle area, which is the same as saying the function does not exist in this interval, right? So, okay, so we can imagine it like this. Now we just have to choose some epsilon for this to work. Now, how the hell do we do that? Well, let's just imagine what this is talking about. So remember, RL is arbitrary. So if we imagine RL, okay, let's expand this graph here, just so this makes a bit more sense. RL, we choose our L on our vertical axis here. Because remember, we're trying to think about the function, right? We're no longer thinking about x, right? We already have x handled. Delta handles x, right? We already figured out that we can find that delta has to be positive, so we can find either a positive or a negative value for our function. L we choose in respect to our vertical axis. So L can be up here, right? If we imagine this as infinity and this is negative infinity, we're just saying, if we go by this statement, that say L is here. Say L is like negative 99, right? We're saying that our function does not exist between negative 99 plus or minus epsilon. So like this is negative 99 plus epsilon, this is negative 99 minus epsilon, right? And obviously the function doesn't exist here. So we're totally fine. So we just have to find an epsilon where we can always prove that x over the absolute value of x is not in the interval. Keep in mind that we're basing this, we can find this based on our delta, right? Because we know that delta is positive, which means we know that x cannot be 0. This is very key. So x can be negative or it's positive, right? So we can always find an x. Here, let me make this a bit more clear. Let's say we have x as like delta over 2, right? If we have x as negative delta over 2, then we know that x over the absolute value of x is equal to negative 1, right? Because this ends up just being negative delta over 2 over positive delta over 2, which is just negative 1. We can also have it as positive delta over 2, right? Because we can choose our x. This is very important. We can choose our x depending on whether we need the function to be 1 or negative 1. This doesn't make much sense, probably, but I think it should click later on. Okay, so what should our epsilon be? Well, we can get a hint is that, this is where we run into trouble. If our L is like here, right? We can't have our epsilon be too large because no matter what, our function is going to exist within this range, right? So we just have to choose an epsilon that's small enough to where we can only have at most one part of our function in there. So we see the distance between this is 2, right? So a very safe number we can use is just 1/2. Because if we imagine L is here, right? 1/2, okay, sure, maybe it gets this, but it wouldn't be able to get the other point down here. If we base L in the very middle, then it only goes up to 1/2, right? And so if we move this, here, this might be a bit easier to... We're saying that, okay, when L is 0, we see that the function doesn't exist within L plus 1/2 and L minus 1/2. This is when epsilon is 1/2. Okay, but here, when L is here, okay, we see that it has one of the parts of the function. But remember, we can choose negative delta over 2 or negative delta over 3 for our negative 1 as our x over absolute value of x, right? Crap. Likewise, when we go down, okay, now it includes negative 1. So we can no longer choose negative 1, but we can still choose positive 1 because positive 1 is not in this interval, right? We know that positive 1 is not in this interval when L is less than, let's say, 0. right? We know that when L is less than 0, we know that 1 is not in the interval between L minus 1/2 and L plus 1/2. Okay, so this is very key. So we know when L is less than 0, right? We can even say less than or equal to 0. We know that 1 is not in this interval, right? Likewise, okay, let me just prove this for you. When L is less than or equal to 0, right? So the maximum function is here. 1 is not within this interval, right? 1 is not in this interval. And if we move down, obviously 1 is not going to be in this interval because, L goes to negative infinity. So in other words, when L is an element of negative infinity and 0, 1, which is equal to x over absolute value of x, is not in this interval. Because we can choose a positive value of x, right? We just choose an x that's positive. Because remember, we're choosing the x. We're taking the x. Okay, but what if when L is positive? Okay, well, when L is positive, we see that -1 can never be in this interval, right? 1 can be, so we can only choose 1. But we know that -1 is not in this interval. In other words, when L is an element of 0 to positive infinity, -1, which we can choose an x for, is not in this interval. And I've been saying in this interval for a long time, but remember that we've proven this is the equivalent statement as this. So if we can prove this is true for some x, like if we can choose an x such that this is true for any L, then we're set. And obviously we have two cases, right? We have a case when L is non-positive and when L is positive. But we can see that we can always choose an x based on that. Notice how we can choose an x pretty late, right? We don't have to choose x before L. If we had to do that, this proof would never work. But we're choosing an x in respect to delta, epsilon, or L, right? In this case, we're going to choose it in terms of delta, and I'll show you why. Okay, so this was a lot of rough work, and hopefully it makes a little sense now. Now we're going to go into the actual proof. Here, let me just shrink all of this. So we found out that we can use 1/2 as a number that works. There are a lot of other numbers that work, right? You could choose, I think you could probably choose 1, actually. You could choose 1 as well if you wanted to. It just makes it a bit less convenient. But okay, so now let's write our proof. Take epsilon as 1/2. Right. So we've checked this off, we checked this off, we checked this off. Now we need to choose an x. But remember, there's no one x that works for every L. We have to have different cases. Okay, so we have a case 1 here, right? Remember, we have two cases for L. When L is non-negative and when L is positive, or is negative. So case 1, L, we can say when L is less than or equal to 0, right? Or we can say when L is an element of negative infinity to 0, right? So when this is true, let's take a look at our rough work. We know that we just choose a positive x. X just has to be positive. Okay, so when we choose an x, we want x to be positive in some way. But we want it to satisfy, we know it satisfies this. As long as x is positive, we know this is true, right? Because we know that we can find, we know that 1 is not in that interval. But we want x to be positive, but we also want this to be true. So how can we do that? So we want x to be positive, but we want x to be smaller than delta. Okay, so delta is greater than 0. So that means delta is positive. We can choose delta over 2, right? We know this is true. So we can take x as delta over 2. Right, so we know del x over absolute value of x is equal to 1. We know, okay, wait. Let's make this a bit more clear. If we represent L plus epsilon, right, we can represent this as an element of negative infinity to 1 over 2, right? Because we were just adding epsilon to both sides. And L minus epsilon is an element of negative infinity to negative 1/2, right? Now we know that 1 is not an element of this interval then. Because we know that we don't know exactly what value L plus epsilon will be. We just know that it has to be within this interval. So we know that 1 isn't in either of these intervals, right? So we know that 1 is not in that interval. So now we're saying, okay, we take a positive x, and we know that x over absolute value of x is 1. So now we can bring it back to our conclusions. 0 is less than absolute value of delta over 2, which is less than delta, right? Check. This is number 1 that we have to prove. And number 2 that we have to prove is that this is not an element of L minus epsilon, L plus epsilon, which we have proven because 1, which is equal to that function, is not an element of this. Therefore, x over absolute value of x minus L is greater or equal to epsilon. Awesome. Now we have case 2. L is the rest. It's positive, right? So now let's do the same thing. Okay, so L plus epsilon is an element of 1/2 and positive infinity, right? L minus epsilon is an element of negative 1/2 and infinity. So we know that negative 1 is not an element of L minus epsilon, L plus epsilon. So now we have to take a negative x. So what if we took negative delta over 2? Does this still work? You're probably thinking no, but remember, we're taking the absolute value of x, right? So, okay, so it follows that x over absolute value of x is equal to negative 1, right? We know that 0 is less than the absolute value of negative delta over 2, which is less than delta. This is true, right? These two are basically the same thing. But now we know that the function is negative 1. So we know that negative 1, which is equal to x over absolute value of x, is not an element of L minus epsilon, L plus epsilon, which means this is true. And notice that we have just proven this for every L in the reals.